Okay, thanks everybody for coming. My name is Geordie Rose. I'm the founder and currently the Chief Technology Officer of D-Wave. We are trying to build a quantum computer, and today I'm going to talk to you about where we're at, the system that we've built, and what it's for. And the particular reason I'm here today is that the system is mature enough to start to use. And so I'm looking for people who would want to participate in using the preliminary versions of this. And to that end, what I'm going to try to do is be as precise as I can about the type of problem that this thing is designed to solve, what might be a good fit and what's not, and try to stimulate your thinking a little bit as to whether or not you may have some problems of this sort that are buried in the types of things you do from day to day at Google. So I'd like to thank Dennis Krupenikoff back there for setting all of this up. Thanks very much. So this is going to have three parts to it. The first is a description of what the system is and what it does. And this is more on the side of what the user sees. So when you actually access the system, what do you see and what can you expect the system to do? Then I'm going to talk about the processor itself, which is the heart of this system, and explain to you, to the extent that I can, how it works. And then I'm going to talk a little bit about what we might expect for performance for the system. Just as a teaser, building special purpose hardware for computing has a spotted history. A lot of times people have tried to build special purpose machines for certain types of problems. And more often than not, those things eventually fail because commodity hardware catches up and passes it. So the reason why you might want to do it this way with this particular hardware is there's a chance that by building processors in this new way that I'm going to describe, you may gain a scaling advantage that you can't compete with classically. So what that means in practice is you may put yourself on a trajectory which is faster than Moore's law and potentially much faster than it, so that commodity hardware can't catch you. In fact, it falls behind you as the technology advances. So the system that we've built has as its design philosophy building a computing system that allows you to pose and solve arbitrary problems of a certain type, which those of you who have theoretical computer science in your background will recognize the words. If you don't worry, I'm going to describe what these things mean. Therefore, a set of decision and optimization problems, which are called respectively NP-complete and NP-hard. So these types of problems are very hard in a sense that I'm going to describe. They're intractable also in a sense that I'll describe, but they're also ubiquitous. They happen all over the place in all sorts of industries, and people have to find ways to deal with them. So this is going to be an alternate way to deal with these types of problems that shares many of the drawbacks of current methods, but it potentially has an upside which is greater than all of them. The system itself has been architected with a constraint in mind. The system itself is big, it's ornery, it has a fridge attached to it, the chips need to be cooled almost to absolute zero, and therefore you have to have a model for use that doesn't require that the machine be sitting right next to you when you use it. And because of that, we've tried to architect the system in a way that's modular so that the user can interact with the system via a web services approach, so that there is some kind of an API that is very well documented and understood, and all you do is you program through that API. And what we're trying to do is to make it so that the system can integrate seamlessly into whatever you're doing. So if you happen to be solving one of these problems using a conventional classical approach, you can yank the solver that you're using out and stick this thing in, and nothing will happen to your existing application. You don't have to change the language you program in or anything like that. So just a brief digression before I go on, because this is kind of a central point to all of this, and I apologize to those of you who know all of this. There's a branch of computer science which is called computational complexity, and the idea is to categorize problems into groups that all share similar features. And one of the most important things you might want to know is that as you feed an algorithm bigger and bigger problems, how does the resource requirement scale? So if you double the size of the problem, how long does, what is the additional time consumption as you do that? And good algorithms tend to be linear or a little bit worse. Bad algorithms are exponential, in which case you get to a point where you just can't solve a bigger problem. So the NP category means this. That may or may not mean something to you. Next slide, I'm going to talk about the way I think about this. And they're all decision problems. So the category of NP means they're problems that resolve to a yes or no answer. So as an example of this, I might ask, is there a path between San Francisco and Vancouver that costs me less than $5 and I'm flying on a plane? So there's a question which has a yes-no answer, and in order to answer that question, might be trivial, but it might be very hard if you have to search through many different possible instances. So here's an example of an NP problem, and it gives you a kind of a flavor for understanding the way these things work. So this is a simple tic-tac-toe game, and you're given some initial position, and the decision question that you're asked is, can O win from this position? So X goes next, and then O, and then X. So each of these trajectories along this direction are particular game instances. You can think of this as moves in chess, moves in tic-tac-toe, decisions that are made that are binary along this chain. So all NP problems have the following characteristic, that for any particular sequence of moves, it's very easy to check whether or not in that particular instance the question is yes or no. So the question, can O win, if you track through one of these paths, in this case you can look at the answer and say no, O did not win this particular instance. So another way to think about that is that given a particular answer, it's very easy to check whether or not that particular answer satisfies your yes or no question. So that's the first thing. The second thing is that there's a possibility that there's an exponential number of these. So if you can imagine every time you have to make a move, like say for example in chess, a total game may only be 100 moves. It's very easy to check who won a game. All you do is you give the moves and you can say, okay, well black won or it was a draw. Whereas the total number of possible chess games is enormous. So these problems also have this feature that the total number of possibilities can be exponentially large. And the frustrating part of these problems is it's not clear whether or not this exponential ends up being a cost that you have to pay in principle no matter what, or if there's a smart way to reduce this. And this is a very tricky and slippery question that people have been thinking about for 40 years, and there's still unresolved issues as to the nature of this type of thing. Now, this particular example is not a hard NP problem, but all NP problems have this kind of nature. So a little bit more jargon. NP complete are the hardest problems of the sort that I just mentioned. There are things for which the canonical version is something called satisfiability. But they have this feature that all problems in this category are mappable to each other with at most polynomial cost. So what this means is that if you can solve one of them with polynomial resources, you can always map to another one and solve that in polynomial resources. So if you solve one of them, they all fall. There are literally thousands of them. The best textbook that I've ever seen on this is a book by Gary and Johnson, which is kind of the Bible of the field. Another important thing about these things is that there's no known algorithm, even with quantum computers, that can efficiently solve these in the sense that you can solve them only using polynomial resources always. There are algorithms that can solve them efficiently, but they don't obey the laws of physics as we currently know them. So if quantum mechanics is right in the way that we understand it, there's no efficient algorithm known. That doesn't mean there isn't one, but we just don't know one of them. NP hard are the optimization versions of these decision problems. So the one I gave before is there a path between Vancouver and San Francisco that costs less than $5? That's the decision version. The optimization version would be, find me the minimum cost for a flight between Vancouver and San Francisco. So they're almost identical in the way you pose them, except you're not asking, is there? You're asking, what is the minimum? And they're very strongly related, but there's a little bit of complexity hidden here in the difference between the two that's not important for this talk. So when you think about NP-hard, all you can think about is it's just the decision problem, but you're asking for a minimum or a maximum. Okay, so given this vast sea of problems that are of this sort, NP-complete and NP-hard, which are literally everywhere, they underlie a lot of quantitative business in all sorts of different sectors, not only just the obvious ones. Question is, how do you create a computing system that will allow you to pose all of this myriad of questions in a reasonably effective way that eventually will be solved on a piece of hardware that we're building? So the way that we've tried to do this is that the hardware itself solves one particular one of these NP-hard problems, and I'll talk at length about which one and how it works. But you have to be able to be flexible enough to use this in all sorts of different other ones that aren't natively that. So the way that we've architected the system, there are web services like APIs at several levels of abstraction. So as a user, you can come in at any one of these levels. And the most primitive of which is that you can say, okay, well, I have a problem and I know how to formulate it as an integer program or a satisfiability problem or something else. So you can go right in and say, solve satisfiability problem, and then just state what it is. And the thing will compile down to the hardware. The hardware will solve it and kick your thing back up. If you don't want to state the problem as in that primitive form, or if your particular problem does not have one of those primitive APIs yet developed, what you can do is go up a level and program in something which is a more commonly used language for interfacing with optimization problems and decision problems, something like AMPL or constraint satisfaction programming techniques. The one that I'm going to talk about a little bit is SQL, standard query language, which we've developed an addition to, which allows you to pose any NP problem. And then above that, you can then consider accessing just applications where all of the underlying stuff has been worked out, and now you're actually using that capability to solve some real-world problem, like a scheduling problem or an optimization problem of some sort that you care about. So there's three ways that this can work. It's architected to be able to be used in all three ways. The first is that you consider that the customer and the data, or the data is proprietary to the customer. They don't want to share it with you, of course. So you have some high-level software that is on that side, and all they need is a browser to access everything that's behind it, which is all residing at the facility where the quantum computer is. All of this stuff is on conventional servers, running some pre-processing and post-processing, and then there's the hardware at the back end. So that's the first way that you can do this. Another way, which is probably the way that it will be done in the short term, is that there will be quite a lot of crunching happening on the user end. So you can download some of the computation onto the user's side for getting the problem ready to be ported onto the hardware. And the third one is, of course, everything in one box. So this is the sort of thing that is not going to be available in the short term because this is quite unwieldy. I'll show you some pictures. But ultimately, that's where we want to take it, so that you can just buy a box. It will sit in the corner. All the software comes with it, and you can use it for whatever you like. Okay, so I want to say a few words about my favorite way to program this thing. It's very simple to use, and I think it clarifies a lot of the issues here. So let's say that you were starting from scratch, and you wanted to build a quantum computer, and you're faced with this issue that how do you get the average person on the street to be able to use it? Because what's going on under the hood is all this quantum mechanics stuff. And a lot of people don't really understand quantum mechanics very well. So the question is, how do you abstract the quantum mechanics away from the user? And I think that you're forced to use a declarative programming language. So what you have to be able to do is provide the user with the ability to state what the problem solution looks like without having to give a prescription for how the machine actually functions step by step by step. So that step-by-step functioning, of course, is required, but you can hide it. So what we looked for were known existing declarative languages that a lot of people knew how to use. And the one that came up as #1 on the list was SQL, standard query language. which is declarative in the way that we need. And it's very easily flexed to the requirements for programming one of these things. So all we did was add a single keyword to the standard lexicon of words you use in SQL, find. Find is very much like select. What you do is you state in the find statement a logical sequence of operators, ands, ors, nots, wheres, all of these sorts of things that define what your problem means. And there's a very interesting thing that has only recently become practical, which is this understanding that the logic captures NP, which means that all NP problems can be posed as logic problems, which is not at all obvious. I mean, that's a very deep thing. And you can use this then to build an interface which is very flexible and easy to use, which we've done and deployed. So going back to the original interface picture, if you come into this and your particular problem is not on this list, which it probably won't be, you can go into SQL, program what you mean, develop an API, and all of a sudden there's a new box here that you created using SQL. And then anybody who comes along can then use that box directly without having to reinvent the wheel. So here's just a short example to illustrate how it works. So let's say you wanted to find an independent set of a graph. So graph is just a collection of edges and nodes. Simple graph right there. An independent set is a set of nodes, no two of which are connected by an edge. So the way that it works in the SQL idea is everything is in database language. So you start out with two tables. One of them is a table of vertices, one of them is a table of edges. And what you want to do is fill in a third table, which is a list of vertices that's the solution to your problem. So when you code this up in the find statement type syntax, you see something like this. So if you're a database programmer, this will basically just read like English. The idea is very simple. You're defining a thing that you want, and you have a set of logical statements that defines what it means to be an independent set. And when you enter this, it will automatically be compiled down to some canonical logic, which is then compiled down to the hardware. So this is what an answer looks like. You get a list of vertices, 1, 3, 5. No two of them are connected by an edge, and you get an independent set. So what are we going to do with this thing? The first thing we're going to do is deploy it in the wild, because there are problems in us actually going out and finding problems like this ourselves. I think it makes a lot more sense for people to come to us, because it turns out that it's very hard to find these things taking a rifle approach. You know, as much as I like to think that these problems are, like I was saying, ubiquitous, it turns out that in practice, usually people avoid these things. You know, they'll have an application or an end goal in mind, and when you look at it in first principles, there's one of these things there, but for some reason it's intractable, so you kind of forget all about it and you go around it and you build something else. Works fairly well. So what we have to do is find ways to make people think deeply about the types of problems that they're solving, and if they had a really effective solver of this sort, would it really matter? And I think that the right way to do that is to provide access to it, 24/7, let people think about it, come back to you, use it, hammer away at it, and see if something comes of it. So what we're planning on doing is providing access to all of this API stuff that I showed, and sponsor collaborative applications development in kind of SourceForge kind of model. And from our perspective, the main thing we want to do is understand why people would want to use this machine, if in fact they do want to use it, which is still kind of an open question. So if in fact people really want to use something like this, what are they going to do with it? Is it going to be image recognition? Is it going to be some kind of pattern matching? Is it going to be a biotechnology application? Is it going to be all of them, none of them, something we didn't think of? And we want to be able to architect the system to be able to scale to literally millions of users. Because I think that if this catches on, there will be applications for which there are going to be millions of users. So you can imagine generic scheduling problems of buses and cities or things like this. We want to be able to capture those opportunities if they come up. So here's the rollout. Next week, the first release of this will happen in the wild. I'm very excited. It's been a long time since we started the company, and it's basically ready to go, which is very exciting for me. And then over the next year, we're going to add more features and scale the thing up. eventually co-locate the machines with the servers that are running the front-end stuff, and then about a year from now release what is probably going to be the first machine that will be able to consistently beat conventional approaches, at least for certain types of problems. And that thing is going to have about 1,000 qubits, and I'll talk about what that means. So just to summarize, the main features of the front end is that the system is architected to be really easy to use. It really is. You know, this is the easiest thing I've ever dealt with to program. It doesn't have a lot of the hard problems that conventional supercomputer approaches have, parallelization and having to vectorize everything and thinking very hard about the details of your code because it matters so much. This is very flexible and easy. You know, all you do is you basically state in logic what you want to have done, and the interaction with the machine is very straightforward. It's about to be released, and it's going to be a very limited release. If anybody wants access to it, let me know. The thing is designed to solve this particular type of optimization and decision problem. Okay, so that was the first part. So now the second part, I'm going to talk about the actual processor itself. So I have one here. This was the generation before the one that we ran the demo on in February. So this is a circa January chip. If anybody wants to see it, you can see it later. I think one of the most amazing things to most people when they see this is that the qubits are actually quite big. So the way that we build these things using these superconducting metals, the qubits end up being visible with the naked eye. And that goes counter to what you may think or have a prejudice towards with quantum computing. You think electrons and photons and all that. The approach that we've tried to take is to stick as close as we can to conventional semiconductor fab, because fabrication of hardware is one of the big bottlenecks to this field. So you can have lots of really crazy ideas about how you might build a quantum computer that end very suddenly when you realize that there's no way to build what you've just invented. So this particular approach has the advantage that you don't need to reinvent the wheel. And why superconductors support large structures that behave quantum mechanically is probably outside of the scope of this talk, but they do, and that's well known. So there's a core concept that underlies the processor design, which is kind of the driving philosophy behind all D-Wave, which is that what we're trying to do is build a piece of matter that through its natural physical evolution solves a hard math problem. So the idea is that you're building an analog computer at kind of the fundamental limits of what nature allows. The way that it works in practice is that the native language of the hardware is what's called an integer program. And the integer program is also known as the Ising model in physics. And this particular problem has this dual feature that you can look at it in two different ways. So integer programming, at least the optimization version of it, is NP-hard. The decision version is NP-complete. These types of problems have serious ramifications if you can solve them efficiently. And I'm not saying you can. I don't think you can. But if you could, a lot of things about the way that computers assist us in our everyday lives would change dramatically. Things that are now intractable or considered to be out of the scope of what you could ever do might become easy depending on how fast the algorithm scaled polynomial. If it was linear, for example, the world would change dramatically, basically overnight. So there's a very clear conception to people who study these problems from the computer science side that they're hard, they're important, they're not simply of theoretical interest, they're also of practical interest, and being able to solve them efficiently would mean significant breakthroughs in all sorts of sectors. Now, if you're a physicist, the model, which is exactly the same thing, so all I'm doing is changing the words, the actual math is identical. This thing is the Ising model, and the Ising model is probably well, it's a pillar of statistical mechanics. It underlies a large amount of the work that's done in modern physics. And basically, it's a model for describing anything where you have interacting components. And this leads me to the one slide that you should remember if you remember none other about the processor, is that the core concept is very simply to build a machine that uses this fundamental laws of physics to solve a math problem in what you can think of as an analog computing manner. So you're building a piece of matter through which just naturally cranking along the way that nature's equations work is attempting to solve a problem which is very fundamentally hard. So when I say building an analog computer, sometimes people have a very strong adverse reaction to that because they're thinking of classical analog computers that have serious deficits. The most commonly noted of which are that the variables that you're using are continuous, and errors are very hard to get rid of. They're not, you can't get rid of errors because they're not naturally digital. Errors are also analog. But what I really mean by analog computer is this, which is really the fundamental definition of what an analog computer is. And in a quantum system, you have natural discreteness that arises from the laws of physics. So when you build a